This video will cover locking mechanisms in operating systems. We will explore shared locks, exclusive locks, and the challenges of deadlocks. By understanding these concepts, you will gain insights into how operating systems manage concurrent access to resources, ensuring data consistency and system stability. Let's understand why locking mechanisms are essential. First, they prevent race conditions in concurrent systems, where multiple processes access and manipulate shared data simultaneously, leading to unpredictable outcomes. Second, locking mechanisms ensure data consistency when multiple processes access shared resources, maintaining the integrity of the data. Third, they coordinate access to critical sections of code, which are segments that must be executed atomically to avoid errors. Finally, locking mechanisms maintain system integrity during concurrent operations, preventing corruption and ensuring reliable performance. Shared locks, also known as read locks, allow multiple processes to read data concurrently. This is beneficial in scenarios where many processes need to access the same data for reading purposes without modifying it. No process can modify data while shared locks exist, ensuring that readers always see a consistent view of the data. Shared locks optimize performance for read-heavy workloads, as multiple processes can read simultaneously without waiting for each other. Shared locks are compatible with other shared locks, meaning multiple readers can access the resource at the same time, but they are incompatible with exclusive locks, preventing writers from modifying the data while readers are present. In database systems, shared locks are commonly referred to as read locks. Exclusive locks, often called write locks, ensure that only one process can modify data at a time. This prevents multiple processes from making conflicting changes to the same resource simultaneously. An exclusive lock grants exclusive access to a resource for modification, ensuring that no other process can access it during the update. It prevents all other processes from reading or writing the resource, guaranteeing that the data is consistent and accurate after the modification. Exclusive locks ensure data integrity during updates by preventing concurrent access and modifications. These locks are incompatible with both shared and other exclusive locks, meaning that no other process can read or write while an exclusive lock is held. In database systems, exclusive locks are also known as write locks, as they are primarily used for write operations. The lock compatibility matrix summarizes how different types of locks interact with each other. As you can see, shared locks are compatible with other shared locks, meaning multiple processes can hold shared locks simultaneously for reading. However, shared locks are incompatible with exclusive locks, meaning that no process can acquire an exclusive lock while shared locks are held. Exclusive locks are incompatible with both shared and other exclusive locks, ensuring that only one process can modify the resource at any given time. Attempting to acquire incompatible locks results in blocking or waiting, where the process must wait until the existing lock is released before proceeding. Now let's explore lock upgrades and downgrades. Lock upgrade involves converting a shared lock to an exclusive lock, allowing a process that was initially reading to modify the resource. However, lock upgrades can lead to deadlocks if not carefully managed, particularly if multiple processes are trying to upgrade their locks simultaneously. Lock downgrade involves converting an exclusive lock to a shared lock, allowing other processes to read the resource while still maintaining some level of protection. Lock downgrades are generally safe and improve concurrency, as they allow more processes to access the resource for reading purposes. Deadlocks occur when two or more processes are blocked indefinitely, waiting for each other to release resources. It is a circular waiting condition that prevents progress. A deadlock happens when two or more processes are waiting indefinitely for resources held by each other, resulting in a standstill where none can proceed. There are 4 necessary conditions for a deadlock to occur. 1. Mutual exclusion. At least one resource must be held in a non-shareable mode, meaning that only one process can use the resource at a time. 2. Hold and wait. Processes holding resources can request more resources, potentially leading to a situation where they are waiting for resources held by other processes. 3. No preemption. Resources cannot be forcibly taken away from a process, meaning that once a process has acquired a resource, it cannot be taken away until it voluntarily releases it. 4. Circular wait. A circular chain of processes exists where each process is waiting for a resource held by the next process in the chain. There are several strategies to prevent deadlocks. Prevent mutual exclusion by using shareable resources whenever possible to eliminate the need for exclusive access. For example, use read-only data structures or copy-on-write mechanisms to reduce the need for exclusive locks. Prevent hold and wait by requiring processes to request all needed resources before execution begins, or release all resources before requesting new ones. For example, acquire all locks at once rather than acquiring them one by one. Allow preemption where, if a process holding resources is denied a new request, it must release its original resources and request them again together with the new one. Implement timeout-based lock acquisition that automatically releases locks if a new lock cannot be acquired within a time limit. Prevent circular wait by imposing a total ordering on resource types, and require that processes request resources in increasing order of enumeration. For example, assign unique IDs to resources and always acquire locks in ascending order. Deadlock detection involves identifying when a deadlock has occurred. To detect a deadlock, use resource allocation graphs to identify cycles, where a cycle indicates that a deadlock exists. Also, periodically run detection algorithms to check for deadlocks and take corrective action. You can also monitor lock acquisition timeouts, where a timeout suggests that a process is waiting indefinitely for a resource. Once a deadlock is detected, recovery is necessary to resolve the situation. Process termination involves aborting one or all deadlock processes to release their resources. Resource preemption involves taking resources away from processes and giving them to others to break the deadlock. Rollback involves returning processes to a safe state and restarting them, undoing the actions that led to the deadlock. In selecting a victim, one should consider the priority, execution time, and resources held by the process. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.